Okay, the rest of the course is based on the following problem. Once you can figure out how to solve this, you're basically done with the course except for a few applications. Here's the problem. We want to be able to compute this definite integral by hand, meaning not using your calculator. Even though your calculator, when you use it, you do use your hand, we want you to do it without the calculator. How would you do such a thing? Well, we're going to use the fundamental theorem of calculus, and there are basically two steps. The first is, given this function lowercase f of x, we want to find a capital F so that the derivative of capital F is the same as the lowercase function f. So given a little function f, we want to find a function whose derivative is that given function. Now, why does that help us? Because now if I have f prime of x equal f of x, I can substitute here f of x with f prime of x. So computing this integral is the same as computing this integral. And by the fundamental theorem of calculus, the integral of a derivative is just the difference in the values at the endpoints. So, and these things I can figure out because I know what capital F is. Let's see an example of that in action. So here I want to integrate from -1 to 2, 2x dx. So I'm looking for a function, so this function is little f of x, and I'm looking for a function, capital F of x, whose derivative is equal to 2x. And if you remember, such a function is given by f of x equals x squared, right? Because the derivative of x squared is 2x. Great. So what that tells us is that now the fundamental theorem of calculus takes over and says that the integral from -1 to 2 of 2x dx, this is my f prime of x, is equal to the value of capital F at 2, that's my b, minus the value at -1. But I know what capital F is. Capital F is x squared. So I plug in 2 into capital F, I get 2 squared. I plug in -1 into capital F, I get -1 squared. And so I get 4 minus 1, which is 3. Okay, so as a check, you should go take your calculator, plug in this integral, and check that you get 3. But we did this by hand without a calculator. Okay, so the hard part of this is to find the function whose derivative is the given function. And sort of this is like a Jeopardy question. Well, in fact, in Jeopardy, the questions are backwards. So Alex Trebek might ask the function whose derivative is 2x, and the question was, what is x squared, right? So we're doing things backwards, and because we're talking about things in the backwards way, we call these antiderivatives. Okay, so a function f is said to be an antiderivative for f if and only if the derivative of f equals little f. Okay, so the derivative of f equals little f. That is, f prime of x is equal to f of x for every x. So the way think about it schematically is we have capital F. If we differentiate it, we get little f. And if we anti-differentiate it, we get back capital F. Okay, so that's what an antiderivative is. It's good to memorize this definition. Finally, I want to point out that antiderivatives are not unique. Not unique. So, for example, what we found is that if we had x squared and we took the derivative of it, we got 2x. Okay, it's something we knew. So that says that x squared is an antiderivative for 2x. This is the little f, and this is the capital F. But I could have used x squared plus 2. So d dx of x squared plus 2, well, the derivative of that, well, it's 2x, and the derivative of 2 is 0, so that's just as good. So both x squared and x squared plus 2 are antiderivatives for 2x. In general, if you have any antiderivative, f of x, you can always add to a constant to it to get another antiderivative. And in fact, any two antiderivatives for a given function differ by some constant. So this constant we'll use capital C to represent. So when you're asked to find an antiderivative for something, you should really add in C. So if I say the general antiderivative for 2x is x squared plus c. So keep adding in this plus c because it gives you the most general form.